Hey, welcome to our unit here on gases. And to begin talking about gases, we need to begin with talking about the kinetic molecular theory of matter. And that sounds super intelligent and makes me feel really intelligent teaching it, but kinetic really just means motion. It means movement. It means motion. So we're looking at the theory of how molecules move, how they move and interact. That is kinetic molecular theory. How molecules move, how they interact, how that defines how that matter is going to behave. So let's look at the kinetic molecular theory. There's some ideas that we need, assumptions we're making when we're talking about gases. And most of our gases that we're going to be talking about, we're calling them ideal gases. And notice what it says. It's an imaginary gas. So it's a fun piece of chemistry where we talk about imaginary things and we do calculations on imaginary gases. Because when we have an imaginary gas, what that means, our ideal gas, perfectly fits all the assumptions of kinetic molecular theory. And what we'll see is that real gas behavior doesn't perfectly fit this. But if a gas is at normal conditions, standard room temperatures, and normal pressures, well then, for the most part, it's going to behave as an ideal gas. It's going to follow the tenets of our kinetic molecular theory. So this is our kinetic molecular theory. So number one here, it says gases consist of large numbers of tiny particles that are far apart relative to their size. So the space that gas molecules occupy, so if the gas molecules are in this container, the volume that they occupy is much, much greater than the volume of the molecules themselves. So when we calculate gas volumes, we don't take into account the size of the molecules itself. It isn't relevant. So say when we look at hydrogen gas, which is H2, and we compare it to CO2, which is also a gas, but obviously we know much bigger because it has carbon and two oxygens. Well, we don't worry about the size difference, about those volume differences, because the space that they occupy, notice what it says here, is 1,000 times greater than the volume occupied by the particles themselves. So once we get into real gases and we pressurize these and we push them closer and closer together, so you can imagine it's a piston and these three molecules are bouncing around, but if we push that piston down really, really tiny, well then their individual volumes start mattering. But when we're talking about the vast majority of our gas law problems, their ideal gas laws, the space they occupy is much, much bigger than their individual volumes. Okay, that's assumption one. Assumption two, the collisions between gas particles, so they're moving around, they're constantly moving, they're constantly colliding, and those collisions are elastic, which means there's no energy lost in the collision. It's not an inelastic collision. There's no loss of energy. There's no loss of, we should say this, like it says in here, no loss of kinetic energy. So it doesn't cause them to slow down due to that collision. We can think about it kind of like if you're playing pool, and the pool balls are colliding. That's generally an elastic collision. There's not deformity to the molecule itself in the collision. Perfectly elastic. So we have elastic collisions. We have volumes that are really tiny compared to their overall volume. The other thing we need to know is they're in constant, random, rapid motion. So all the gas molecules, they always have kinetic energy, and they're always moving and interacting and smashing into each other. Now, number four, there's no forces of attraction or repulsion between our gas molecules. Well, guess what? We already know that's not really true, right? Because we know that even non-polar gases have temporary or induced dipoles, and thus are going to have van der Waals forces. But we're saying when we are doing gas law problems, those are such small forces that unless, again, we're under extreme conditions, they do not matter. We're going to ignore those. So for kinetic molecular theory, we're making tons of assumptions. We're assuming the gases are in continuous random motion. We're assuming they have perfectly elastic collisions. There's no loss of kinetic energy in collisions. There's zero attractive forces between them, no intermolecular forces. And, again, we assume that the volumes they occupy are much, much larger than their own volume. So we ignore their own volume. Okay, last one, which I think is the most important one, and one we don't think about very often, but so critical, is that the average kinetic energy of a gas molecule depends on the temperature. Actually, we can say this, that measuring the average kinetic energy of gas particles, if we measure this, that is temperature. Temperature is a measure of the average kinetic energy. So notice, just from 9th grade physical science, kinetic energy is 1/2 mass times velocity squared. Well, this essentially, I'm not going to use an equal sign because they're not in the same units, but that essentially is proportional to temperature. Okay, so let's think about this a second. So I'm zooming it really in because this is important. This is proportional to temperature. So kinetic, and this is the average kinetic energy, so I'm going to write average of all the gas molecules. So we can't just look at one, but the average of all of the kinetic energy, the average kinetic energy of all the gas molecules in a sample is proportional to the temperature. Temperature, again, is actually, if we scientifically define temperature, temperature is a measure of the average kinetic energy of the molecules. So if we look at the individual molecules, well, their mass isn't going to change, right? We can't change the mass of a molecule. They're not going to get heavier or lighter. So in that type of idea, what is temperature? If molecules have a high temperature or a low temperature, what is it? Well, it is purely dependent on one factor, the velocity of the molecules. If those molecules move faster, they will have a higher temperature. If we heat a substance up, its molecules move faster. So we have to get that link in our head, that's very important. That velocity and temperature of the molecules are linked. They are kind of temperature is really a measure of how fast those molecules are moving. We call it a measure of the average kinetic energy, but it's really a measurement of how fast those molecules can be moving around. Obviously, things that are colder, there's less motion. Things that are hotter, there's more motion. So what we can use is we can use the kinetic molecular theory to explain a lot of the behavior of gases. Again, notice, like it says, even though we don't have ideal gases, nothing behaves perfectly by those tenets as long as we're not at really high pressures or really low temperatures where things start sticking together and interacting more. So you can imagine if you push molecules all together or get them really cold so they all start sticking together. These are supposed to be gas molecules, not a happy face. If we get them really close together, well, then all those things are going to fall apart. But as long as we're not at intense pressures or intense temperatures, then our kinetic molecular theory will work to explain most of the behavior of gases. So, going through behavior of gases here really quick. Gases expand. They expand to take the shape of the containers. So like it says here, if you take a 1 liter vessel that's filled with a gas, transfer it to a 2 liter vessel, that gas will quickly occupy that space. Okay, fluidity. So gas particles don't have a lot of interactions with each other, so they can slide past each other. They can move past each other fairly easily. There's not any sticking going on. Those are the elastic collisions we talk about. Gases have very low densities because, again, they occupy huge spaces in relation to the size of their individual particles. And also because they occupy such huge spaces, gases can be compressed. We can force them down into smaller and smaller volumes of containers because they occupy such vast volumes anyway. What else? They diffuse and they effuse. And these are two words that are so to know the difference. Diffusion is the mixing of two substances caused by their random motion. That is diffusion. Effusion is one sample of gas moving across a barrier. So diffusion, two things moving together. Effusion, one gas crossing a barrier. So here is an example of diffusion, two gases mixing. One thing we want to notice when we look at this is look at the types of molecules we have. We have hydrogen, and we have oxygen over here, and also nitrogen. Well, oxygen and nitrogen are bigger molecules. So when we open, notice the stop cock is closed. Need to take a breath after that one. That's kind of difficult for me. And then we open it. Well, the two gases are going to diffuse, is the word. They're going to diffuse, they're going to mix. Now, those rates of diffusion are dependent on one thing, based on the molecules. Well, it's dependent upon temperature. Higher temperature, everything will move faster, and so they'll diffuse faster, but it's also dependent upon the mass of the molecules. And so if we look at this, notice the hydrogen, there's more hydrogen that diffuse into the second canister than there's oxygen and nitrogen that diffuse back there. Why? Eventually they should all spread out and be equal, but initially the hydrogen is lighter, so it diffuses faster. So our diffusion rates are really based on two things. They're based on molecular mass, molar mass, and they're based on temperature. So the higher the temperature, the faster the rate of diffusion, and the lower the molar mass, the faster the rate of diffusion. We'll look at those calculations later. So finally, what are some deviations from ideal gas behavior? Well, and that would be called a real gas. Well, like we said, at very high pressures, this is probably the statement we want to remember, at very high pressures and very low temperatures, basically our gas molecules start to stick together. Okay, so their kinetic energy, once they get super close, their kinetic energy can't overcome the attractive forces that are between the molecules themselves. One way we kind of know this is we know this based on a lighter. So everybody has their cigarette lighters at home, probably in their pocket right now, waiting to get outside. Actually, everybody probably smokes e-cigarettes now. I don't know if you need a lighter for your e-cigarette. I don't know how they work. I'm old. Back in my day, we smoked real cigarettes with real flames, and we were real cool. Nowadays, I don't know. Anyway, so everybody has their lighter. Well, inside your lighter, when you look inside your lighter, you'll notice there's a liquid on the bottom of your lighter. Normally, they have it in two different areas there, but it's a liquid, right? Well, that liquid is propane, C3H8. And what happens when you depress the button? Well, when you depress the button, you let it out. And when you let it out, guess what? It's a gas. C3H8 spreads out, and it's a gas, and it'll behave as an ideal gas. But inside, it's at extreme pressures, or high enough pressures to force the gas to interact with itself and to stick together. So its kinetic energy inside the lighter is not sufficient to overcome the attractive forces between the molecules. So that gas, when under really high pressures, turns into a liquid. And when we get down close to that point, so a lot of gases are compressed to that extreme point where they'll actually turn into liquids. When you get close to that point, well, then that's the borderline where gases stop acting as ideal gases and start acting as real gases and start interacting with each other. Another kind of caveat to this, and let me erase that mess that I was writing, is this, that kinetic molecular theory is more likely to hold true for gases that don't have any type of dipoles. So if we're talking about helium, neon, they're going to be more ideal. But if we get into things that are polar gases, like ammonia, or notice water vapor, they're going to deviate more from ideal gas behavior because they have polarity, so they're going to stick together more. So if we have completely non-molar polar molecules, things like noble gases, for one, or even diatomic gases, those are going to have more ideal behavior over a wider range of conditions. If we get into things that have some polarity, well, then their ideal conditions are going to be much narrower, and they're going to deviate from that a lot quicker. Okay, so a couple quick questions here that I want to look at that I think are important. Two factors that van der Waals proposed to explain why real gases deviate. Well, they deviate, again, at two major conditions: really high pressures, right, and really low temperatures. Okay. Which of these gases would you expect to deviate significantly from ideal behavior? Well, I would expect hydrochloric acid, water, and ammonia, because those are all polar, right? The other ones are non-polar. So because they're polar, they're going to deviate more significantly from ideal behavior than things that are non-polar molecules, because they're going to interact. So they're not going to have those perfectly elastic collisions and everything we talked about with our kinetic molecular theory. A big idea to remember for this lecture is that temperature is a measure of the average kinetic energy of a gas. So these are proportional, right? The kinetic energy is proportional to the temperature. So if the temperature goes up, the kinetic energy goes up. And what else is actually going up at the same time? Well, the velocity of the gas. So temperature is tied to molecular motion. That is kinetic molecular theory.